Dear students, a warm welcome to massive open online courses in chemistry on SWAYAM. I am Dr. Amrita Anand. In the previous module, you have learnt in detail about adsorption, absorption, physisorption, chemisorption, their characteristics and applications of surface chemistry. In this module, we will discuss about the process of catalysis, its types, mechanism and applications which play an important role in surface chemistry. After going through this module, you would be able to define catalysis, to classify catalysis into homogeneous and heterogeneous catalysis, to explain enzyme catalysis and its mechanism, to state the role of catalyst in industry. What is meant by catalysis? Let me explain. Potassium chlorate, when heated strongly, decomposes slowly, giving dioxygen. The decomposition occurs in the temperature range of 653 to 873 degree Kelvin. This can be represented by the equation 2KClO3 giving 2KCl plus 3O2. However, when a little manganese dioxide is added, the decomposition takes place at a considerably lower temperature range, that is 473 to 633 degree Kelvin, and also at a much accelerated rate. The added manganese dioxide remains unchanged with respect to its mass and composition. In a similar manner, the rates of a number of chemical reactions can be altered by the mere presence of a foreign substance. The systematic study of the effect of various foreign substances on the rates of chemical reactions was first made by Berzelius in the year 1835. He suggested the term catalyst for such substances. Substances which accelerate the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalysts, and the phenomenon is known as catalysis. You have already studied about catalyst and their functioning in the modules on chemical kinetics. It is important for you to know about promoters and poisons. Promoters are substances that enhance the activity of a catalyst. For example, in Haber's process for manufacture of ammonia, molybdenum acts as a promoter for iron, which is used as a catalyst. The corresponding chemical equation is given here. According to this, dinitrogen reacts with dihydrogen in presence of iron and molybdenum to yield ammonia. The action of a promoter may be due to the formation of a compound between it and the catalyst. This may help to enhance the adsorption of substrate on the catalyst. Poisons are substances which reduce the efficiency of a catalyst or decrease the activity of a catalyst. For example, barium sulfate acts as a poison for palladium in Rosenmann's reaction to selectively reduce acyl chloride to aldehyde. Thus, over-reduction is prevented. Catalysis can be broadly divided into two groups, homogeneous and heterogeneous. First, let us talk about homogeneous catalysis. When the reactants and the catalyst are in the same phase, that is liquid or gas, the process is said to be homogeneous catalysis. The following are some of the examples of homogeneous catalysis. Number 1, nitric oxide acts as the catalyst in the lead chamber process for the manufacture of sulfuric acid. As given in the equation, sulfur dioxide gets oxidized to sulfur trioxide with dioxygen in presence of catalyst. Sulfur trioxide is then converted into sulfuric acid. In this, the reactants sulfur dioxide and dioxygen and the catalyst, which is nitric oxide, are all in the same gaseous phase. Number 2, hydrolysis of methyl acetate is catalyzed by H plus ions furnished by hydrochloric acid. According to the equation, methyl acetate is hydrolyzed because of water in presence of hydrochloric acid to give acetic acid and methanol. As you can see, both the reactants and the catalyst are in the same liquid phase. Number 3, hydrolysis of sugar is catalyzed by H plus ions furnished by sulfuric acid. The appropriate equation is given for your reference. An aqueous solution of sugar reacts with water in presence of sulfuric acid to give aqueous solutions of glucose and fructose. In this case also, the reactants and the catalyst are in the same phase, that is the liquid phase. Number 4, the equation shows the decomposition of ozone using atomic chlorine as catalyst. Ozone and chlorine are in the same phase, that is gaseous phase. Number 5, oxidation of carbon monoxide to carbon dioxide using nitric oxide as a catalyst. The equation shows that carbon monoxide reacts with dioxygen to give carbon dioxide. As is evident from the equation, both the reactants and the catalyst are in the same gaseous phase. Now coming to heterogeneous catalysis, the catalytic process in which the reactants and the catalyst are in different phases is known as heterogeneous catalysis. Some of the examples of heterogeneous catalysis are given here. Number 1, oxidation of sulfur dioxide to sulfur trioxide in the presence of platinum according to the equation. The reactants are in the gaseous state while the catalyst is in the solid state. Number 2, combination between dinitrogen and dihydrogen to form ammonia in presence of finely divided iron in Haber's process. It is clear from the equation that dinitrogen reacts with dihydrogen to give ammonia using iron as the catalyst. The reactants are in the gaseous state while the catalyst is in the solid state. Number 3, oxidation of ammonia into nitric oxide in presence of platinum gas in Ostwald's process. As is clear from the equation, the reactants are in the gaseous state while the catalyst is in the solid state. Number 4, hydrogenation of vegetable oils in presence of finely divided nickel as catalyst. Vegetable oils react with dihydrogen in presence of nickel to yield vegetable ghee. In this case, the reactants are in liquid and gaseous states, but the catalyst is in the solid state. Number 5, conversion of ethene to ethane in presence of platinum, palladium or nickel. It is the process of hydrogenation. Ethane reacts with dihydrogen to give ethane. Here the reactant is in the gaseous phase and the catalyst is in the solid phase. Number 6, the chemical equation given shows the reaction between carbon monoxide and hydrogen to give methyl alcohol in presence of copper and zinc oxide as catalyst and chromic oxide as promoter. The reactants are gases and the catalyst and promoter are solids. Number 7, decomposition of hydrogen iodide on gold catalyst to produce molecules of hydrogen and iodine is shown in this equation. Catalyst gold is in the solid form and the reactant hydrogen iodide is in the gaseous form. Adsorption theory of heterogeneous catalysis. This theory explains the mechanism of heterogeneous catalysis. The old theory known as adsorption theory of catalysis was that the reactants in gaseous state or in solution are adsorbed on the surface of the solid catalyst. The increase in concentration of the reactants on the surface increases the rate of reaction. Adsorption being an exothermic process, the heat of adsorption is utilized in enhancing the rate of reaction. The catalytic action can be explained in terms of the intermediate compound formation, the theory of which you have already studied in the module on chemical kinetics. The modern adsorption theory is the combination of intermediate compound formation theory and the old adsorption theory. The catalytic activity is localized on the surface of the catalyst. The mechanism involves 5 steps. Number 1, diffusion of reactants to the surface of the catalyst. Number 2, adsorption of reactant molecules on the surface of the catalyst. Number 3, occurrence of chemical reaction on the catalyst surface through formation of an intermediate. Number 4, desorption of reaction products from the catalyst surface, thereby making the surface available again for more reaction to occur. Number 5, diffusion of reaction products away from the catalyst surface. These steps are well illustrated in the diagram. The surface of the catalyst, unlike the inner part of the bulk, has free valencies which provide the seat for chemical forces of attraction. When a gas comes in contact with such a surface, its molecules are held up there due to loose chemical combination. If different molecules are adsorbed side by side, they may react with each other, resulting in the formation of new molecules. The molecules thus formed may get desorbed, leaving the surface for fresh reactant molecules. This theory explains why the catalyst remains unchanged in mass and chemical composition at the end of the reaction, and this is effective even in small quantities. It, however, does not explain the action of catalytic promoters and catalytic poisons. Let us consider the important features of solid catalyst. The first and foremost feature is activity. The activity of a catalyst depends upon the strength of chemisorption to a large extent. The reactants must get adsorbed reasonably strongly onto the catalyst to become active. However, they must not get adsorbed so strongly that they are immobilized, and other reactants are left with no space on the catalyst surface for adsorption. It has been found that for hydrogenation reaction, the catalytic activity increases from group 5 to group 11 metals, with maximum activity being shown by groups 7 to 9 elements of the periodic table. The second important feature is selectivity. The selectivity of a catalyst is its ability to direct a reaction to yield a particular product. For example, starting with hydrogen and carbon monoxide and using different catalysts, we get different products. As is evident from these chemical equations, the same reaction yields methane when nickel is used as the catalyst, methanol if copper zinc oxide is used, and formaldehyde while copper is used as the catalyst. Similarly, ethane is obtained on hydrogenation of ethine in presence of platinum as catalyst. But when palladium and barium sulfate poisoned with quinoline is used, ethene is obtained as the product. Same is the case with sulfur, which is known as Lindlar's catalyst. Thus, it can be inferred that the action of a catalyst is highly selective in nature. That is, a given substance can act as a catalyst only in a particular reaction and not for all the reactions. It means that a substance which acts as a catalyst in one reaction may fail to catalyze another reaction. Now, let us learn about the other important part of surface chemistry, which is shape selective catalysis by zeolites. The catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and product molecules is called shape selective catalysis. Zeolites are good shape selective catalysts because of their honeycomb-like structures. They are microporous aluminosilicates with three-dimensional network of silicates in which some silicon atoms are replaced by aluminum atoms, giving ALOSI network. Due to a network of tunnels and cavities, the surface areas inside the solid are large. Generally, the size of the pores varies in the range 260 to 740 picometer. Therefore, only those molecules which have sizes smaller than the pore size of the zeolites can enter and leave the pores. The reactions taking place in zeolites depend upon two factors. Number one, the size and shape of the reactant and product molecules. Number two, the pores and cavities of the zeolites. Zeolites are found in nature as well as they are synthesized for catalytic selectivity. Zeolites are widely used as catalyst in petrochemical industries for cracking of hydrocarbons and isomerization. An important zeolite catalyst used in petroleum industries is ZSM5. It converts alcohols directly into gasoline, that is petrol, by dehydrating them to give a mixture of hydrocarbons. Next, we will study about enzyme catalysis. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of high molecular mass and form colloidal solutions in water. They are very effective catalysts that catalyze numerous reactions, especially those connected with natural processes. Number of reactions that occur in the bodies of animals and plants to maintain the life processes are catalyzed by enzymes. The enzymes are thus termed as biochemical catalysts, and the phenomenon is known as biochemical catalysis or enzyme catalysis. Many enzymes have been obtained in pure crystalline state from living cells. However, the first enzyme that was synthesized in the laboratory was in the year 1969. I now tell you about some of the examples of enzyme catalyzed reactions. Number 1, inversion of cane sugar. The invertase enzyme converts cane sugar into glucose and fructose. Number 2, conversion of glucose into ethyl alcohol. The zymase enzyme converts glucose into ethyl alcohol and carbon dioxide. Number 3, conversion of starch into maltose. The diastase enzyme converts starch into maltose. Number 4, conversion of maltose into glucose. The maltase enzyme converts maltose into glucose. Number 5, decomposition of urea into ammonia and carbon dioxide. The enzyme urease catalyzes this decomposition to give the required products. Number 6, in stomach, the pepsin enzyme converts proteins into peptides, while in intestine, the pancreatic trypsin converts proteins into amino acids by hydrolysis. Number 7, conversion of milk into curd. It is an enzymatic reaction brought about by lactobacilli enzyme present in curd. These details along with the sources are tabulated for your ready reference. What are the characteristics of enzyme catalysis? Enzyme catalysis is unique in its efficiency and high degree of specificity. The characteristics exhibited by enzyme catalysis are: number 1, highly efficient. One molecule of an enzyme may transform 1 million molecules of the reactant per minute. Number 2, highly specific in nature. Each enzyme is specific for a given reaction. That is, one catalyst cannot catalyze more than one reaction. For example, the enzyme urease catalyzes the hydrolysis of urea only. It does not catalyze hydrolysis of any other amide. Similarly, urea can be hydrolyzed only by urease and not by any other enzyme. The unusual specificity of enzymes is due to the presence of active sites on the surface of the enzymes. During the reaction, the molecules of substrate, that is a reactant, bind to these active sites by means of hydrogen bonds, dipole forces or other intermolecular forces of attraction. Number 3, highly active under optimum temperature. The rate of an enzyme reaction becomes maximum at a definite temperature, which is called the optimum temperature. On either side of the optimum temperature, the enzyme activity decreases. The optimum temperature range for enzymatic activity is 298 to 310 Kelvin. Human body temperature being 310 Kelvin is best suited for enzymatic reactions. Number 4, highly active under optimum pH. The rate of an enzyme catalyzed reaction is maximum at a particular pH called optimum pH, which is normally between 5 and 7. Number 5, increasing activity in presence of activators and coenzymes. The enzymatic activity is increased in presence of certain substances known as coenzymes. It has been observed that when a small non-protein, maybe a vitamin, is present along with an enzyme, the catalytic activity is enhanced considerably. Thus, the vitamin is a coenzyme. Activators are generally metal ions such as sodium, manganese, cobalt and copper. These metal ions, when weakly bonded to enzyme molecules, increase their catalytic activity. Amylase in presence of sodium chloride, that is Na plus ions, is catalytically very active. Number 6. Influence of inhibitors and poisons. Like ordinary catalysts, enzymes are also inhibited or poisoned by the presence of certain substances. The inhibitors or poisons interact with the active functional groups on the enzyme surface and often reduce or completely destroy the catalytic activity of the enzymes. The use of many drugs is related to their action as enzyme inhibitors in the body. What is the mechanism of enzyme catalysis? Two models are proposed by biochemists to explain enzyme action. Number 1, log and K model, and number 2, induced fit model. We shall see these one by one. First, let us see log and K model. There are a number of cavities present on the surface of colloidal particles of enzymes. These cavities are of characteristic shape and possess active groups such as amino, carboxylic acid, thiol and alcohol. These are actually the active sites on the surface of enzyme particles. The molecules of the reactants, that is substrate, which have complementary shape, fit into these cavities just like a key fits into a lock. On account of the presence of active groups, an activated complex is formed, which then decomposes to yield the products. This is explicitly shown in the figure. Thus, the enzyme catalyst reactions may be considered to proceed in two steps. Step 1, binding of enzyme to substrate to form an activated complex, E plus S giving ES hash. Step number 2, decomposition of the activated complex to form product, that is ES hash giving E plus P. Now, let us come to induced fit model. It is shown by spectroscopic and X-ray crystallographic studies that when a substrate molecule reaches the active site, the enzyme changes its shape to accommodate the substrate. It is this ability of the enzyme to change its shape that determines whether or not the reaction will take place. According to this model, the substrate induces the active site to change in order to fit the substrate, unlike in the case of rigid log and K model. As shown in the figure, it can be imagined as a hand in a glove, in which the glove, which is the active site, does not get its functional shape until the hand, that is the substrate, fits into it. We now see the applications of catalyst in industry. Some of the important technical catalytic processes are listed in the table to give you an idea about the utility of catalyst in industries. These processes have already been explained at various places in the module. Let me recap the essential points for your benefit. A catalyst is a substance which enhances the rate of a chemical reaction without itself getting used up in the reaction. The phenomenon of using catalyst to increase the rate of reaction is known as catalysis. In homogeneous catalysis, the catalyst is in the same phase as are the reactants, and in heterogeneous catalysis, the catalyst is in a different phase from that of the reactants. The catalytic reaction that depends upon the pore structure of the catalyst and the size of the reactant and product molecules is called shape selective catalysis. Zeolites are good shape selective catalysts because of their honeycomb like structures. Enzymes are complex nitrogenous organic compounds which are produced by living plants and animals. They are actually protein molecules of high molecular mass and form colloidal solutions in water. They are very effective catalysts that catalyze numerous reactions, especially those connected with natural processes. Two models are proposed by biochemists to explain enzyme action. Number 1, lock and key model, and number 2, induced fit model. Catalysts have wide and important utility in various industries. In the next module, we are going to discuss about colloids, classification, preparation of colloids, and micelle formation. Thank you.